in stage because whatever you do with your material, you need to find ways to see what happens. Especially when you grow a material, sometimes it's easy to put some powders inside the components and to grow something, but you need to know what you're getting. So that's why when you start, when you start the characterization, the first question that you need to ask yourself is what type of information you want to get. You have a material at a specific time, and you need to ask yourself, what do I need? And I'm saying that because sometimes I see from my students that they come to me and say, okay, let's do XPS, let's do TEM, L06, whatever. They give me a full list of characterization and say, okay, do all what you need. But the basic question is, what do you need now in order to continue? Because usually when we grow something, we don't reach a final step in which everybody applauses and the work is done, right? So we grow something, and then we need to continue. We had a question before the experiment about the growth, and we try to answer, and we might be answering that question, but on every growth we'll have 10 different questions. So therefore, we need to channel our energies in order to answer them. So what information do we need? So when we are talking about materials in general, and some parameters here in particular about 2D materials, so first of all we need to check that the material that we are targeting is the material that we are obtaining. And this might sound trivial, but sometimes it's not trivial at all, because sometimes you're growing materials that they may have different phases. Of course, one more stable than the others, but you need to ensure that the material that you're growing is the one that you're targeting. And then, of course, in the 2D materials, we saw how the number of layers influence and impact the properties of the material, and therefore we must know what the number of layers that we have is the thickness. Now, quality is something that everybody wants to know. What is the quality of our material? And this is a big question. How do you define quality? How do you define quality? How do you define quality of the material depends very much on the application that you are targeting. If you are targeting, for example, catalysis, you may need the nanocrystals or even defective crystals that will give you a lot of catalytic sites. If you're targeting optoelectronics, you may need a single crystal material with less as possible density of defects. So quite the opposite. In the catalysis, you may need multi-layers. Here, you need single layers. So quality is a very tricky work. You need to be careful with it and define it as much as you can to yourself. And of course, chemical composition is related to the phase, but it also includes doping, impurities, alloying that you may have, etc., etc., etc. And based on that, after you ask your question and answer these ones, pick the properties, the information that you want to get from the characterization, so then you can decide what characterization to use. Another important parameter in the day-to-day work in the lab is how fast I can get that, right? Because when you're growing a material, and if you decided that you're going to do TEM, but if the next TEM spot is 2 weeks from now, so what next? Are you going to sit drinking coffee till the TEM spot is available? No, right? And sometimes when you're growing materials, you need to know very fast what the outcome, even if not the complete picture, but at least some information. So again, you need to define to yourself what is the information that you need fast, and what is the information that you can or you have no choice and you need to wait to get it. So that's why the first tool that I will show you is the optical microscope. Yes, the optical microscope that many labs, even in high schools, have, can be very useful to characterize the materials. Like the Scotch tape that many offices have is very useful to isolate single layers, right? Sometimes unexpected things happen. And it's amazing that in the beginning of the field, it wasn't so clear, and many people argued that it's impossible to identify or to see single layers on top of substrates. And it makes sense. I mean, why should you identify single layers on a substrate? It doesn't make any sense. But the fact is that you can do that. Of course, you can do that, and it's very useful. As you can see here, an example of a flake, of course, by exfoliation. Usually, when you exfoliate the material, you get many flakes on the substrate with many different number of layers, which in this case is very convenient because then you can show all together. So you see that at the edges, we were talking about, at the edges of the exfoliated flake, you can localize single layers, and then you have thicker layers. And how many layers you have? If you have, you can see that in the optical microscope by, for example, comparing the color contrast between the surface and the different layers. Thicker the material, more reflective it becomes, and therefore you see it brighter. Thinner the material it appears darker than the substance. And therefore, if you take this and plot the contrast, you analyze this image, plot the contrast, this is more or less what you will get. Of course, the thinner films again are darker than the substrate, the thicker or brighter.
So,
yes.
there is no linearity in the process because more layers having little more high contrast compared to the layer of trade.
One layer is here, the layer. So I guess that the reason for that, maybe it's a mistake here because the 3 layers and the 2 layers are labeled the same. But I think that part of that is as you add layers, the reflection starts to become significant. As you can see, the thickness. So I think that's why it's not just a linear relation. And then how it works, there are many papers describing that. Basically, what happens is that the contrast calculation is a bit complicated because we are talking about thin materials that are lying on top of a silicon dioxide layer with a specific thickness on top of the silicon substrate. Of course, the contrast that I showed you was the silicon dioxide silicon wafer. If you put the sample of different substrate, you will get completely different results. Here you can see the contrast for the different number of layers and for different thicknesses of silicon dioxide, so, which is a critical parameter. Here you can see basically the calculation for the contrast, which is the intensity coming from the 2D minus the intensity of the subset, of course, divided by the sum. And then you can plot, basically, you can take a lot of measurements, different wavelengths, and different thicknesses, and plot the, here you can see the wavelength, of course in the visible, as a function of the silicon dioxide thickness, and on the 3D, the color basically is the expected contrast. And as you see, there are very specific places that you have a good contrast. Now, a good contrast is the one that will allow you to identify the layers, to see the layers. Okay? And that's why it's very important to be on one of these lines in order to make an easy identification after you exfoliate your material. And the same works for many other 2D materials, very similar. And the funny thing is that so the Novoselov group, when he exfoliated for the first time in 2004, he didn't know that. He just took the wafers that they have in the lab, I guess. Maybe they try different wafers, I don't know. But the wafer that gave them the wafer that they used is the one that gave them the biggest contrast. So then it was relatively easy to identify for the first time a single atomic layer of graphene. Take into account that at that point nobody did that before, so they didn't even know if it's possible. Okay, but it's possible, and if you're on one of these lines, right? So that means that we need something like 285 to 300 nanometers thickness of silicon dioxide, or 90 nanometers or 100 nanometers of silicon dioxide. If you do it on a different thickness, like 150 nanometers of the silicon dioxide, you will see the single layers will be very, very hard to notice. So here you have the tool, a very simple tool, that you, right after the exfoliation, you can check immediately to see if you have the material that you're looking for. Let's say that you're looking single layer. So you can look for the single layer in the optical microscope, and then if not, so then you make another exfoliation. Okay, so this is very fast, very convenient, and that's why it's very common, and that's why it was so heavily analyzed. So what happens when we have a different substrate, right? So this is on silicon dioxide silicon, which is okay, and we saw the contrast behavior. What happens when we do that on different substrate? Here you can see the example of CVD bonded graphene on top of copper. And again, this is optical microscope. So how come that you see a single atomic layer of atom, a single atomic layer of carbon on top of graphene? Any ideas? What is the color difference? Is the color of the graphene? Here is the graphene. This is the color of the graphene.
Actually, graphene is optically transparent. It's in mono. How many layers? It's optically transparent.
Single layer.
So it's optically transparent.
Yeah.
So obviously,
so how come that you see the color difference? Material scientists, where are they? what do you have on top of the surface of the copper, remind me? What happens to a metal when you expose it to the air?
Oxide forms.
So you have some oxide.
Oxide.
And this is the reddish thing. The brighter part is the copper color, which is protected by the graphene. So oxidation is much slower. So if you take the sample after a few days that you synthesize the graphene, you will see something like that. And that's why you can identify where the graphene is and where not. So what information can you take from this? First of all, what it looks like, first of all, this is what is called the sub-monolayer, right? So you have there is no full layer, you have isolated domains. The domains are very clean, about a centimeter, and apparently single prism, although this you need to check by other methods. And so therefore you can check by this simple optical microscope, if you know, but you need to know your material, you need to know your sample, right? And by that you can check very fast the coverage. You can check if you have, for example, a full layer, right? If you synthesize a full layer of graphene, and you still see spots of oxidized copper. That means, for example, that you have defective graphene. Okay? If you have a perfect graphene, high quality graphene, the copper will be oxidized much slower. Okay? So this is another example. You don't need to go to the SEM. You should go also to the SEM. This is something that you can get right after the growth. You can expedite, by the way, the oxidation. If you really need to know if you have a continuous screen, if you really need to know how was the growth, you can take out the sample and put it, for example, in a hot plate at low temperatures. The graphene can stand the high temperatures. So, but the copper will be oxidized faster. And again, when you are checking two areas, the kinetics are the ones that are important for you. So here the oxidation is much slower, here much faster. So therefore you can differentiate between simple, very simple. Another way also with optical microscope, but in this case with another addition in the optical microscope. So are you familiar with dark field? Dark field is basically, in order to do dark field with the optical microscopy, you need objectives that support that, of course. So in the bright field, basically the light comes down and is reflected back to the microscope in order to see it here, right? Binoculars. In the dark field, the path in the center is blocked. So then you have light only at the edges, okay? That comes to the sample when you focus, comes from the side, like making a conus, right? So therefore, if you have a very flat surface, you will see actually this black. You don't see anything. If you have a very flat surface. If you have asperities on the sample, even nanowires, nanoscale objects, they will scatter the light, and you will pick them. Some of it you will pick. And therefore, it's a very good method, even in optical microscope, to see if you have even nanoscale objects in your sample. And why am I telling this? It is not sensitive enough to detect a single atomic layer. But but in this case you don't need it. So what happens here is again. So what you have here is a single layer domain on top of copper. This is bright field. You see almost nothing. You can see almost nothing. Okay, very hard to see anything. But if you do the dark field, this is what you will probably see. What are you seeing here? You are not seeing here the graphene. Again, also before we didn't see the graphene. We saw where the graphene is, where the copper is not oxidized. So it's like an indirect way to characterize the material to see that the material is there. So in this case, the same. It's not that we are seeing the graphene because of this dark field, but we are seeing what is underneath the graphene. What do you see here? Are you familiar with this? So what happens? So these are usually metal foils. Okay? Metal foils are materials that are polycrystalline, right? Every grain is a single crystal, but on different crystal orientations, random crystal, unless you do a specific crystal. So let's take this crystal. So then you have this crystal, and therefore you have many different crystal orientations, and some of them low index. If you are not familiar with the term, please ask. Some of them low index planes, but some of them are high index planes. And high index planes and also low index planes actually, they have on the surface, so let's say that this is the low index plane and therefore the low energy plane, okay? If you are in the high index plane, that means that you are deviated from the low index plane, okay? With an angle, which is this signal angle, the Mister angle, right? So now, what will happen to the surface? This is a higher energetic stage, right? A higher energetic plane. So what the surface does in order to minimize the energy, in special when you do a heat treatment, you basically provide a thermal energy, like in the case of graphene. So the substrate tries to minimize the energy as possible, meaning that he tries to be at the low index plane as much as he can. But because of the miscut, he cannot be at the low index plane, and therefore steps are formed. Steps or facets are formed. So this area is low index, so low energy. But then you have these areas that are higher energy, of course. But overall, we reduce the energy of the surface compared to the high index plane, right? So now we have steps or facets that are, in these cases, are a few nanometers high. And this is perfect for a dark field optical microscopy. Because these steps you can see in the optical microscope. And now you're asking what happens here? Why you don't see anything? Because again, the graphene protects the surface. The graphene stabilizes the steps longer. When you expose the surface to the air, these steps are gone. Okay, even very mild oxidation that we don't see by eye, it will kill these nanofacets or nanosteps. But the ones that are underneath the graphene are present. And these are the ones that you're seeing here. So again, this is an indirect way to check, to see that we have a graphene layer.
So what is the step size typical step size?
There is no, well, typical size could be sub-nanometer to few nanometers usually. So some of them you don't pick. The sub-nanometer is very hard to pick. I don't think that you pick it. But in the rest of the polycrystalline material, you will find a lot of places with the nanofacets. So if you see the nanofacets, you know that you have graphene. So this is another indirect way to check for graphene. So therefore, optical microscope is very good for, well, thickness depends very much on what substrate, if it's silicon or other, a coverage, add layers, and of course just the presence. This is sounds trivial, but anybody that deals with growth, especially with the growth of something new for the first time in the lab, you need to check that he's getting the material. That's the first question. Am I getting the material? Not how good is it, how large is it. Am I getting the material? This is the first question, right? So this can answer to that very fast by being working behind this. So Raman, it turns out, and this fact to the scientists that were doing 2D material science back in the 70s or 80s, they didn't know that apparently. They didn't quite. Also, the Raman systems were less sophisticated than the ones that we have today. Anyway, Raman spectroscopy is a very, very good tool to characterize most of the 2D materials, not everyone, not anything, most of them. Here you can see the case of graphitic material. So again, the reciprocal space with the energy dispersion, and then the Raman signal. Here you have the different modes, the IR active and the Raman active modes. And here you can see the characteristics signal for many types of graphitic materials. Oh, sorry, carbon materials. For example, sp3 amorphous carbon looks completely different. Okay? What is relevant for us, of course, is the graphite that looks here. There are three main peaks. There are many others, but three main peaks that we usually take into account. And they are called the D peak, which is supposed to be here. I will explain why we don't see it in a minute. Then the G mode, which is this mode. And then the 2D or G prime mode, which in graphite, in AB stacking graphite, it has a specific shape with the shoulder because there are two components contributing to this. And it turns out that, first of all, the cross-section signal of Raman in the graphitic materials, and also in many of the other 2D materials, is very strong, probably because of the covalent, some covalent bonds. And what you see here is the characterization of the two different peaks that changes dramatically with the thickness, with the number of layers. One of them is the 2D. Okay, you remember the shoulder that I showed you before of the graphite. There are two main components contributing to this, and then reducing the thickness to two monolayer will change it completely because here you have only one component. So it's an isotropic peak and very sharp if you have morphine, high quality morphine. On the other hand, the D band, which I didn't show you yesterday before because that spectrum came from a material with no defects. The D band got the D name because it is a signal that is triggered by defects. The Funon mode in the D band is basically the stretching of the hexagon, right? So as a result of that, if the lattice is perfect, they just cancel each other. Therefore, you don't detect any defect. If the sample has very low density of defects, you don't have defect. But if you have a defect, say a point defect, so then it becomes a triggered and active. And it appears that this were numbers. Therefore, as you can see, Raman in morphic systems, in spatial, but also in some of the other 2D materials, is very good in order to identify and prove, not only prove that you have a single layer. Even if you came from the optical microscope with something that you think, believe, that according to the contrast is a single layer, you put it now in the Raman, so you should get a very specific Raman spectrum. Okay? And so, yeah, which is this spectrum. And this spectrum is coming from a defective graphene. Look at the diptych. The diptych is huge. But a few things you can learn from this spectrum. First of all, that you have single layer. Why? Because the ratio between the intensities here, the intensity of the G mode, which is the stretching of the in-plane stretching of the hexagon, and it's not sensitive to the number of layers, it's sensitive to many other things that we'll see in a second. So the ratio between this intensity and the G prime intensity that is very sensitive to the number of layers should be very small. One should be usually twice or more bigger than the G. Now, maybe because of the diptych here, this ratio is a bit different. Now, the diptych here shows you that you have a lot of defects, but that the sample is very crystalline, because otherwise you will get a broader picture. And the thing about spectroscopies in general, very general, any spectroscopy, sharper the peak means that the material is of higher quality. Why is that? Because the signal that you're measuring, it doesn't matter if it's a Raman signal from a specific mode or another spectroscopy, the signal that you're measuring, if it comes with a very narrow distribution in this case in the Raman sheet, so that means that they are all coming from the same type of events. Right? If you have slightly different events, for example, in the Raman modes, if you have some defects, so the Raman modes, the vibrations will change slightly, and you will see that by broadening of the peaks. So in any diffraction, in general, sharper the peak that you measure usually by full width half maximum, full width in half of the height of the peak, is an indication, a first indication of the quality of your material. And in this case, a good graphene, first of all, should have no diptych, so very small diptych, ratio of G to G prime very, very small. Less than half.
So, is there any hard and fast rule that for multi-layers always the defects will be more? Like in the previous slide, so it was blue shifted, right, for multi-layers compared to.
So what did you say?
So, is there any hard and fast rule that always so actually the peaks were broadened when it is multi-layers. The peaks were broadened. So it is only because of defects, as you said.
No, the peaks here are not necessarily broadened. Take a look also how they squeeze on the peaks. That's why you need to check the full width at maximum.
The full width has improved. Going
as you improve the quality of your material, it should improve. Yes, it should be smaller. The full width.
Yes, but yeah. So is there any hard and fast rule that for multi-layers always the defects will be more? If you take a highly crystalline material and you are growing.
I'm not sure that for multi-layers the defects will be the density of defects will be higher. Why do you say so?
But because the peaks were broadened, right? The full width maximum improved, right? So that's what I'm saying.
No, but in this case, the contribution to this peak is coming from several events. Here, there are two different peaks contributing to this G prime. So you cannot compare between that. If you compare also, take one of the contributions and calculate the full width maximum. You need to decompose the peaks in the analysis.
So there are various G points.
In multi-layer, you have several contributions to the G prime, which is the 2D band. Yes, in the single layer, you have only one.
G prime.
And that's also a characteristic signature of a single layer profile. But you need to be careful. Because if you have a multi-layer profile or even a graphite that is completely turbostratic, you remember turbostratic that all these layers are rotated. When you rotate the layers, you basically increase the distance just a bit, increase the distance between the layers. And this causes sometimes to look like a single layer. So you get a single peak. It's like you isolate, basically. Even if you have a graphite, you isolate the layers. So you have multiple single layers. But in any stacking, you should get the above.
Microscopic and stage, but if you use optical microscope in that case.
Optical microscope, what?
Like in that case, if there are multiple single layers, we can see through an optical microscope.
No, in the optical microscope, you will see a graphite.
Multi-layer.
Yeah.
Only contrast you can see, not.
In contrast, in the optical microscope, you don't see any difference.
Yeah, that's right. So even though if you get a single layer here,
Right.
then you can find a single layer.
Right. So always you need to combine. Always you need to combine between different methods. Always you need to verify yourself better with different methods. So then
How are
you
you indexing it actually? Because those two are two different machines. So you are physically changing the sample from one instrument to another.
carry the
Yeah.
sample.
So
It will be
after
the same
that,
sample.
how are you locating the exact place where
Okay, there are many techniques for that. You may pattern the sample with alignment marks. You may do any other sign. There are many ways to do it.
okay, so this will be inbuilt with the optical microscope. Like patterning during the optical microscope?
No, you can for example do the exfoliation on a pattern on a sample that has alignment marks, for example. There are other students they find a way. I also used to.
You can also.
There are many ways
You
to
can
it.
also mark by like profilometer. Also can make a line. There are many ways.
I never did that.
There are many
Don't
ways.
you destroy the profile?
Like not destroying. Like you can make a nano level line through AFM. Also can contact me. You can make.
No, don't use my AFM to make scratches on the surface. Okay. So this is about single layer profile. Now another piece of information information, very important piece of information regarding the DP is that you cannot compare the intensity of the DP between different samples just by measuring the intensity of DP in this sample and then comparing the DP in another sample. What you need to do is to compare the ratio between the intensities of the P and the G. And this is a measure of the relative density of defects. It cannot give you, it's not a quantitative, it doesn't give you a number. But when you compare different samples, it shows you which sample has a larger density of defects and smaller. And if you want to get deeper into the theory on that, it comes from a work like done 10 years ago by House group, where they basically took a graphite and made defects by ion shooting, the ion beam. And then they measure the distance between the defects, and then they measure the different ratios. Very interesting theory. Anyway, this is the way to compare between the samples. And but with Raman you can do more than that. As I told you yesterday, you can use it to study the growth mechanism, as it was done for graphene on copper or nickel, right? Nickel bulk diffusion and segregation, copper surface mediated growth, and you can see that you can basically elucidate the growth mechanism by ex situ method, by one, in this case, Raman method. Okay? So you can use the Raman by many other things, not only counting the number of layers and estimating if your sample is high quality. Another thing that was proved very nicely with the Raman, and this is regarding the G mode. The G mode is the mode of the vibration in plane of the hexagon. And the G mode is not sensitive to the number of layers, but is sensitive to a lot of other things. It's sensitive to strain, it is sensitive to charges, and therefore, for example, here you can see that the Raman was used to monitor the doping in a graphene device. So what you have here is the graphene transistor. Okay? A piece of graphene shows in grain. The silicon dioxide is our dielectric layer. So we have a backgate, a heavy load silicon. So in this case, this is with a gated solution. Okay, so not that, no backgate. Maybe also backgate. They have backgate by the solution, by a unique solution. And what they show is, first of all, they check the transistors. This is how a transistor behaves, where you have the I as a function of the B gate, and you can identify different doping regimes, and then of course the IPDS, which is linear in so this is called the charge neutrality point, okay, where you are supposed to be, is where the graphene has the lowest conduction, the lowest current. At the center, at the leading point, at the K point, at the joining point between the two points in the secondary structure. Anyway, then you can once you characterize the device and it works, it should work, you can start doing Raman in situ, applying analyzing, in this case, you can see the G mode and the 2D mode, the G prime mode, as a function of the gate of the this voltage, is the top gate voltage. And you can see that the G mode moves according to the charge density. Larger the voltage, larger the shift of the G mode. Larger the G mode position, as you can see here very nicely. So this is for zero gate, no gate. So this is our starting point. And from that, you see how it changes dramatically. So it can be used also to monitor changes in another field that is very useful. Is I mentioned the intercalation, right? Intercalation is very interesting. Intercalating materials, compounds, molecules, atoms in between graphite plates is very interesting. And what is one of the ways to check that you have a good intercalation by Raman? Because the intercalants, one of the triggers for intercalation is charge transfer. And charge transfer is very sensitive to a G mode. So when you can estimate the quality of the intercalation, so how much of the intercalant you have in, by the G mode position, basically shift. Okay?
Sir, one thing. So the curve shifted left side, and then again it is shifted to right side, right? So what it indicates, like after certain voltage?
No. We start from this point. This is the zero.
Okay. So charging.
Once you charge it, it doesn't matter if holes or electrons, you get the same shift or similar shift to the G mode. So the G mode is not selected to holes and electrons.
So, sir, as you said, G mode is a result of exciton stretching, right? So, exciton stretching in the beginning slide, you said G mode is because of the exciton stretching.
No,
like you showed on hexagon, right? Hexagon structure. So,
it's not an hexagon. G mode is a Raman mode, which is a vibration mode in the hexagonal pattern.
So that is because
it's the mode that deals with the stretching of the hexagon.
In plane hexagon.
Yeah, but not exciton. Has nothing to do with hexagons.
So because it is also looking at the charges, right? So exciton is also a combination of two charges, right? So why can't it give the exciton information? That's why I'm surprised. When it is dealing with the charges.
I'm not sure that it can. I'm not sure. Maybe it can. I don't know. Okay, so what about other methods of course? So the graphene is classical, it's very good tool, and for other materials it's also useful, maybe not as useful as for graphite materials, but it's very useful as well. And here you can see the Raman spectrum for an MOS2 as a function of number of layers again. And you can see that there are differences, not a lot of difference like we saw earlier, but one characteristic feature of a single layer MOS2, for example, is that the difference between the peak position, the P2G and the A1G of in MOS2, it gets lower than a 20 centimeter minus 1 for a single layer. So this is a proof that you have a single layer. By the way, the same in graphite, in graphene, and in MOS2, if you have defects, if you have impurities and a lot of other things, they may change the spectrum of the Raman in such a way that you cannot then be sure that you have a single layer, but you may have a single layer. For example, a very defective profile will not give you the ratio of a single layer of a high quality single layer profile give you so therefore you need to also be careful with that. Yeah, here you can see this modeling and measurements for the different for three different for two different DMDs and its alloy. Okay, so you can see that in the alloy you can see so so in principle Raman and yeah. So Raman also is a very good method I showed you before in the data structures that you can have different compositions in qubits and you can have also lateral vertical lateral structures. And these are things that you can identify both in Raman. Here you can see the Raman in this work where they give basically alloys of sulfur and selenium monolayers. You can see the Raman spectra from when X is 0. So you have only the sulfide. So this is the sulfide and how it switches. So here you have the alloy and then you have only the molybdenum, the selenide. And the same you can see in the PL spectrum, right? It changes according, as I showed you before, so it changes according to the composition, these days of selenium, the relative composition of selenium. Another thing that you can do with Raman is to monitor strain. Not only this is for TMDs, but you can do that also in the graphene. Basically, what you do then is you transfer your single layer to a flexible substrate, and then you can stretch it, for example, and measure the strain, or you can bend it and also measure in situ the Raman. And by that, you can basically know the percentage of the strain and check the Raman, and you see that the Raman changes dramatically. It's expected that the vibrations of the lattice will change when you have strain.
So this A1 and EG peaks are always when we apply the strain.
Again?
This A and G, EG peaks.
This is L06.
A and E.
Yes.
Always is when we apply the strain.
Yes.
A and G peaks.
There is a splitting of the peak. That's what you mean?
No, that is because of the strain only. Always.
Yes.
A and E peaks. The labeling, I am asking, the labeling of A and E is always when we apply the strain.
There is a mode that it splits with the strain.
Splits the strain.
Yes,
but
because think about that. You have hexagons, right? So you basically now have elongated hexagons. So you have two main directions: the in-axis direction along the strain and the vertical one, which are very different in distance. And that impact the vibration in these directions.
So those are known as A and E. Those are known as A and E peaks.
Yes.
So, sir, I read that A and E peaks are when they are sharper. So, the indirect way of finding exciton binding energies, the peaks of A and E.
Always you go back to the exciton binding energy.
Yes, sir. Actually, we can indirectly say from these peaks, like if their peaks are very sharper, so then there is probability of excitonic states at that point. That's what indirect way of.
Okay, so here you have another thing to check with the Raman.
Can I make a comment? Concept of exciton will come if you have a different charges bound to the single state, right? If all the electrons are having the same charge, so how can we consider this as an exciton? That is the case, all the electrons which are
strain creates, when the strain creates, so at that point the probability will be exciton is a combination of two charge.
Yeah, but opposite, right? It's not like the same charge in a bound state we cannot call as exciton.
But in the literature, there's an indirect way of measuring exciton dynamics.
So same charge in a bound state we cannot call as exciton.
Same charge in what?
Two electrons nearby in a bound state, we cannot call it as an exciton.
No, exciton is a combination of electron and hole.
What? So hole is in the formation of electron hole.
Yes, the electron hole state.
No hole.
Bi-exciton, so two elements in hole.
Suppose if you consider two metals, P and N material, then there is a.
But here completely graphite, right?
No,
I'm
not asking here. I'm in general.
You see, in general, if there are two different
Layers,
charges, then there will be.
Yeah, that's what I'm asking.
Okay, so therefore, we can see that Raman spectroscopy is very good for two materials in general, and graphite materials, of course. It's been studied for tens of years, but also in these materials have, most of them have very strong signals that arise from the strong voltage. There is one material that does not, that Raman is not so useful. This one is the hexagonal boron nitride. Hexagonal boron nitride, I forgot to add this. Hexagonal boron nitride has one peak in the range of 1365. One peak, only one peak. In contrast to graphitic systems that you have several peaks, so you can compare between them, like the defects, like the relative intensities of the G and G, or the relative intensity of G and 2D. In HBN, you have only one peak. That when you reduce the HBN to a single layer, this signal is extremely weak. And the signal should be in the single layer. The only indication for being a single layer is that it should shift by 5 wave numbers to 1370. That's it. That's all what Raman can tell you about HBN. And that's why that is one of the reasons that in contrast to graphitic materials and TMDs, it is very hard to characterize single error HBN. Because in order to do so, you need to go to other methodologies that are time consuming and not something. There is nothing fast as Raman that is so efficient. And that is detrimental for the growth process, for the growth development. And we see that the growth of HBN is less advanced, let's say, than the film. Okay. Okay. So a bit about, I guess that you are familiar with this scanning electron microscope. Scanning electron microscope, we have a field division of an electron beam that we basically focus and manipulate with a set of magnetic and electrostatic lenses to the surface, and then when the electron hits the surface, this is better. When the electron hits the surface, a lot of things can happen. A lot of interaction happens simultaneously. Of course, every interaction has its energy range and its characteristics. So we can, in principle, study any of these interactions in order to extract some information about the material, chemical information, morphology, etc. etc. You can see here the most known interactions are the secondary electrons that happens only at the few nanometers range in depth, and then deeper than that you have the backscatter electron. These are the two main detectors in every SEM, which is so the secondary electron interaction is sensitive to the surface, while the so then it's to the surface structure morphology, and therefore and the backscatter electrons is sensitive to the atomic number of the atoms. So therefore, it gives you a way to differentiate between different materials. And then from deeper areas, of course, you can get X-rays, photoluminescence, and many EDX, characteristic X-rays, of course, that are useful for elemental chemical composition. So again, so here you can see the comparison of, I think, backscatter electron detector SEM on the left, and optical microscope that you already saw. And you see again that we have a very strong contrast. And again, the question is, how do we explain that?
Charging effects.
The secondary electrons, despite the fact that it's sensitive to the surface, to the surface means few nanometers deep, not to the atomic layers. So how it comes that we have such a good contrast between the graphene domains and the substrates?
Charging effects.
Charging effects, yeah. But the copper is a very good conductor.
But it also comes from oxide.
The oxide, yeah. The oxide, this is the reason. We have an oxide. That is for even with an oxide that we don't see in the optical microscope is enough to allow for the big contrast. And of course, if you put the graphene on top of the silicon dioxide layer substrate, you will see also huge contrast. So even though you have a single layer, a single atomic layer, it's very easy to see this in SEM. Now again, compared to the methods that we saw basically, so you see here the same domain, right? The same domain on copper. So here we have the bright field optical microscopy that we don't see almost anything, the dark field that we can detect where the graphene is. And also in the SEM, we see, but in the SEM, we add now another piece of information. What do we have here? This is an add layer, a second layer, okay, that actually goes usually below. Okay, second layer of graphene that you can identify. Look how sensitive it is to the number of layers. In dark field, most of the times you cannot see it. But this is Raman mapping. So in Raman mapping, of course, you can identify where the graphene is, where you have double layers, and so on. So if we need to compare between all these, again, the dark field is a very good option to give you a 5-minute answer to what we have what the basic material that we have. SEM, it gives you another piece of information, but that's it. And the Raman gives you the proof that you have a single layer. By the way, not here and not here, you can be sure that you have a single layer. Most probably, because this is how the graphene works. This is not a proof that you have a single layer. So the Raman can give you all together. It gives you the coverage, it gives you the number of layers, the add layer and the single layer are very easily distinguished. It gives you the quality of the material by seeing we have a diptychs and the nature of the peaks in terms of the sharpness. So, but the disadvantage of the Raman is that tens of microns scanning takes quite a lot of time, right? While this takes 2 minutes, and this, well, it depends how long you wait for the spot. But if you have a spot now, it will take you an hour. And another big difference is that because of the time consuming, the Raman mapping is good for relatively small areas, while the other two methods are very good for very large areas. Okay, so you need always to combine between the methods in order to address all these issues. Okay, another thing, very interesting thing that you can do is by special detectors. We're not getting to the details of that. But for example, if you take TMDs, on the regular 1H configuration, and if you rotate them or move it one across the other, you will change the symmetry of the material, and therefore you will create constant charges, and you will induce basically ferroelectricity by just moving these TMD fields. There's a professor at the University that published many of these, and he called it sliptronics, because you slip the layers and you get different electronic properties. And by using special detectors, you can detect basically the different charges and the different atomic configurations on the surface, as you can see here. Okay, the same, by the way, if you do another more precise methods like AFM method that measure charges, so you can also get the same images, AFM more specifically. And so by SEM, using this detector is not so simple. You can in principle detect all these slips in between the layer, misregistry between the layers that gives this beautiful arrangement. Okay, and then the other option is, of course, transmission electron microscope. In transmission electron microscope, instead of eating the electron beam, you need now to transmit the electron to the other side. So here's the specimen. The specimen will vary depending on the method that you're using, but you transmit the electron through the specimen, and therefore there are some critical issues with the specimen. You cannot put any sample, right? You need to put a sample that is thinner than 100 millimeters. And if you want the total resolution, it must be much thinner than that. Now, for our materials, it's not a problem because our two materials are inherently few atoms thick. And so then, in order to study our materials in the TEM, what you need to do is, again, you need to transfer from the material from the substrate, from the growth substrate, to what is called the TEM grid. So this is what from one of the companies that deals with that. And there are many different TEM grids. The TEM grid basically is a grid of metal, usually copper, that has holes, of course, And on those holes, usually in special for our films, there is a membrane or a carbon membrane or a very thin membrane with holes. The idea that this membrane has holes, so you put the TMD or the TMD or the 2D on top of this membrane, and you can study that in the theater. But then, of course, as you may imagine, these TM grids are very thin and very sensible. You need to be very careful, and the yield of the success in transferring atomic layers to these TM grids is not always great. You need to practice a lot. Here you can see an example of a grid. I think there's a silicon nitride grid, and what you see here, these are domains of tungsten disulfide. You see that sometimes they just break, fold, and then you have some areas. These areas are covered by a single atomic layer, so the triatom membrane.
So instead of transferring on a grid, suppose if we etch the substrate to 1 micrometer, in TM typically 1 micrometer thickness they allow, right?
No. So 1 micrometer in TM is a lot.
Thickness I must substrate.
It's a lot.
If you can reduce it to up to a few 0.5 micrometers.
There are ways to reduce it, but you will not be able to reduce it enough to get an atomic resolution. If you want atomic resolution, you need to suspend it.
Suspend.
And also, I'm not sure that reducing the thickness of the growth substrate is much easier than transferring. It's also challenging.
Yes.
So then once you have this, you can do TEM imaging, as you can see here, and these point defects, I couldn't find the movie. These point defects that you see here, basically most of them are sulfur deficiencies. These were not here. My samples are not so defective. But while imaging, you see that. You see how the holes are created as time passes. So you need to be very careful in studying. Here you can see even the line defect. Basically, there are people that in situ created such defects in order to study them in situ in the TEM. Okay. So yes, so in TEM,
what is the time scale of heat changing? Let's say if defect percolates. So heat change in which time scale?
Seconds.
Second? Within second?
You know why? I don't remember. I need to find the movie. I don't remember if he did that. I don't remember. I didn't do the TEM. I had a collaborator in the Roseman Institute, a very good TEM scientist that did it for me. We had a movie showing the initial layer that was almost without defects, and then suddenly.
So if you could not mention this, share that with us. We want to see the real time scale we want to say.
Yeah, I need to check the movie. I don't remember where I put it. I couldn't find it. I wanted to show it here. I couldn't find it. I can check it.
Because I want to match that with the molecular dynamics simulation of the symmetry.
But I'm sure that there are papers about that. People studied that. People studied the defect formation and then manipulated all kind of defect, all kind of streams, and also saw the holding of the defect. You can see the defect moving all along. People have shown that. I mean, have published that. We didn't publish. We just were analyzing our samples. and yes, and you don't see the images here, but these are TMDs that are folded into nanostructures, and you can see the bed. Okay, in this screen you cannot see many details, but anyway, it's very useful. And of course, if you combine that with chemical analysis, like energy dispersive spectroscopy, which is about X-rays basically coming from the same onion interaction. And with others, things I showed yesterday, basically you can show you can get a full picture of what you have here. So this is the imaging, and then you do the chemical analysis, so you can be sure of what phases you have in every place, right? And here another example of axial indium selenide on top of MOS2. So the indium selenide is this multi-layer crystal, and the MOS2 is here at the bottom, and you can see it's easily seen by the mapping of the elements, as you can see here, the molecules, and sulfate only at the bottom.
Sir, this is cross-sectional time.
This is what?
Cross-sectional time, right?
Cross section, yeah.
Please explain how to prepare sample.
Okay, cross section. For this specific sample, the best way to do cross section is by focused ion beam. Focused ion beam, what you do is it's also a complex process, but of course many people do that today. So what you do, so you start from the material, let's say top view of a plate, whatever that you want to do cross section. So first of all, you need to deposit on top of it a protective layer, and you need to choose the protective layer according to the materials that you have in the layer, so they don't confuse in chemical analysis. Protective layer, and then you need basically to start digging with the focus ion beam. So it's very energetic, and sometimes it causes a lot of defects. But when you do it right, so you prepare a very narrow lamella. Okay, so basically you take the sample and you need to scar by the ion beam, and then rotate it and scar. And then you need something to catch it, to catch the lamella, and you cut, basically you disconnect the lamella from the substrate, and then with the manipulator you place it on the TEM grid. You basically take it like that, and you rotate it so the cross section is parallel to the plane of the TEM grid. And then you put it in the TEM and you measure.
So what would be the height of the lamina?
Well, it depends on your sample.
It should be
Yes.
So what should we mean, right? Like actually the width of it now.
And it will be tens of, I would say, 100 nanometers, maybe more. That's why you have a protective layer. You deposit the protective layer. Right? It gives what? It has two main reasons. One is to protect the layer from a lot of things that happens on the surface, and also it gives rigidity and mechanical support to the lamella.
Basically,
Because you have also the part of the substrate that you have. Okay? So I don't know exactly what is the minimum thickness.
So here also pattern transferring only, sir, in the vertical also, like in the horizontal we suspended layer, right?
Oh,
In
yeah.
in
Then you take this lamella. Let's say that. Let's say that this is the lamella. Okay, this is the substrate. Okay, so I scared and made the lamella and take it out and place it on the TM grids. So the cross section, so this cross section is now upwards. So then we can come with the TM, right? TM with the electron beam. This is how you make this. Also, it requires some more. And lastly, okay, EBS mapping, of course, gives you a lot of answers to the elemental composition of your materials, which sometimes, especially when you deal with data structures, is extremely important. And then the important thing also is to that you have the possibility to do electron diffraction. So electron diffraction gives you basically the same information that X-rays diffraction will give you on bulk samples. But in this case, it gives you on the nano scale. So what you can see here is basically electron diffraction from this sample. Okay? So you have an hexagonal lattice, single layer, single crystal in the area of sample that gives you only one hexagonal pattern, okay, in the diffraction. Now, if you do the same diffraction in an area where you have domain boundaries, so you have 2 or 3, 4 boundaries meeting together with different orientations, so then you will see 3, 4 different hexagonal patterns which are rotated according to the angle, the relative angle of the lattice, the lattices. Okay, so this is also a very good method to check the twisted PV layers, to check exactly the angle, for example, of the layers. And also, you know, in order to be sure that the phase that you're measuring, the structure that you're measuring fits the pattern, so what you need to do is to measure the spacing between the peaks, and then there are ways to calculate from that the plane that is giving this diffraction, and you calculate with you compare that with databases in order to, and you know what materials you have in your sample. It's much harder to identify material that you don't know if it's on your sample or not. But if you know what material you're looking, it's fairly easy. Okay, questions? Yeah.
You are talking about reducing strain by stretching the substrate.
For example, yes.
The force between the substrate and sample is one.
Well, you're right. So you need to be careful with that. But it's not stable. But if you have polymers, you might be able to catch it, at least at the low strains. People have them.
How can I expect the same strain is applied to a sample? Because substrate may have some strain, but I cannot expect my 2D also will have the same strain, because they're not actually connected with each other.
Well, this is a very good question, because you need to be careful that the 2D material is not slick, it has very low friction. But again, these are polymers, and people have shown that. So how they verify that the 2D indeed has the same strain, I'm not sure, but they measure the strain by one. I mean, there was some strain, so maybe the percentage that they're showing there is not accurate.
So the interaction between the suppose if you have 2 different layers like MOS2 and WS2. So when we place layer by layer stack, so the interaction between the layers, what's happening at the interface of the 2 layers, that also has very significant device properties. Any other, it also not only exotonic, I'm saying there are other properties also, like forces in between the layers, and also how the charges are distributed at the interface.
Well, how the charges are distributed are also dependent on the registry between the domains. That's exactly what is twistronics, all this field of twisting layers and testing the electrical properties. Also, the interface will differ if you have defects, for example. If you have point defects, you may have anchor points. You may change completely the properties, the interface. It's a big issue. question? Okay, thank you.